start? Wait a minute. It's still white. Right. So first, our minor, which will be on Monday, I think 15th March, slot H. So we shall do it at 3 p.m. Okay, 3 p.m. So everybody should be ready a few minutes before, and it will start at 3 p.m. and you will have some 40 odd minutes for it. Okay, and it will be such that you can score fairly good marks. And I hope that we only have the top 4 grades as we discussed in class 1, the first class, right? Now, what is left for us to do before the minor? The first thing that we have to do is, you see, we were discussing flow through packed beds. I have derived the correct equation, which is there in your slides. However, it was a more phenomenological derivation. The equation is correct, but now I want to extend it today to a force-based derivation, because in the other topic that we did, we started out with force-based type of Newtonian mechanical approach. So we should continue in that vein for this flow through packed beds also. So that's something that I want to complete. Let us see by today or at most tomorrow. And then based on what we have derived by this force approach, we will have a final equation which you can use to predict many things on packed beds. For instance, pressure drop for a bed of particles. So now to actually use those pressure drop equations, we will need some charts, like you had the chart for the drag coefficient for free settling over 10 decades of Reynolds number. You will need similar chart now for packed beds. Of course, the range of Reynolds number of hydrodynamics is not as wide as for free settling. I think we would have it over 5 decades of Reynolds number, from say 0.01 to 1000 or something like that. And I would also have to give you those graphs or correlation. That's something that I shall give you tomorrow. Okay, I have to find the, and actually I have it in various handbooks, but I have to photograph it and then we put it on your slide list, right? So these are the two things that we need to do to complete and extend that derivation based on our usual force approach, which is a more interesting approach for me from my point of view, and then give you the modified curve with modified Reynolds number, including the epsilon factor over 5 decades of Reynolds number, so that you can use these formulae by reading those charts and then calculate various things like pressure drop through the packed bed for any flow of any Reynolds number or modified Reynolds number, which will include the 1 minus epsilon or 1 minus e fraction, right? So this is really what we need to do before minor 1, which will be on Monday 3 p.m. So you have to be ready. I'll also post on Teams to everybody. So please spread the word. So let us share the slide. Wait, the slides have to still appear. Okay, these are still the old ones. Right, this was the the correlation I just mentioned. You see this type of diagram. You will need an analogous diagram. See this diagram that you have. This is only valid for settling under gravity, right? Or in a centrifuge, whatever. But similarly, we have to come up with another chart for packed beds, which will be posted tomorrow. And that will be then the end of what we want to do for the minor. Now, yeah, this was the hindered settling chart. That's the other chart. You see, this was the hindered settling case that I also covered with epsilon as the void fraction for a uniform bed. Okay, fine. And here, this is really what we defined because our correlation is in terms of dm prime, which was a mean diameter based on the void volume and the surface of the particles, right? So this is what we defined. And if S was the specific surface area of the particles in meters squared per meter cubed for all the particles in the packed bed, then dm prime was related to voidage and the specific surface area by equation 6. Okay. Then this led to the equation which I call Kozeny equation, all of which started from Darcy's law. Okay, we started from Darcy's law, a very simplistic form. Okay, and then we have derived this equation for pressure drop and mean velocity through the bed of solids in terms of all the various parameters such as the length of the bed, the specific surface area, the voidage, the viscosity of the fluid, and the Darcy's law constant, or what in this case is called Kozeny's constant, K prime. Strictly speaking, it is dependent on shape of the particles, but for spherical particles, this is indeed a constant. I shall come to it. But first, we must try and improve this derivation. And I mean, we must start from the basic force balance and derive the same equation. So what I have asked you to do exactly. So can also derive by force balance. That's the topic of today. So you have to somewhat think how we can do this. I mean, I already outlined it to you. I mean, we spent awful lot of time. I mean, we can't keep spending that much time on each and every subtopic, right? I mean, we spent a lot of time on the force-based approach, where we included all the forces and defined these things for settling. Now, how should we do that for this particular application? That's my question. In other words, next slide is, we have to derive this Kozeny and Darcy's and Kozeny's type equation using force balances. And I shall indicate you the solution, but please think on it right now. So what you have to do is to consider the forces acting on the fluid in a packed bed of a certain cross-sectional area, which we can take it to be unity for convenience, and a certain length or thickness L. In particular, we are interested in the drag force because all our correlation even earlier was based on the drag force or the drag coefficient. So we will similarly, we want to have on the y-axis a derivative of that drag force term or some component of the drag force term acting in the direction of the motion. See, there the motion was perpendicular, I mean, was vertical, so it was fine. But here, let us see how we can derive that component, which I call r prime, which is generally called, given the notation r prime, which is the drag force per unit area of the particle surface in the direction of the flow. So see if you can worry about all the forces that are acting on the fluid in the packed bed of unit cross sectional area and length L, and how the pressure drop is going to balance that drag force essentially. That's what I would enjoin you to try and work out now, and I shall indicate it to you, and we can then further develop the solution. There are so many various developments you can do, and not all of which I want to cover. Okay, as I said, I have written on the slide indicate solution. So maybe I can outline the steps and then you can try further. So basically, we want to plot a component or the friction factor or drag coefficient or a component of the r prime, which is the drag force per unit area of the particle surface. We want to plot that on the y-axis. And on the x-axis, we want to have the Reynolds number, but in this case, the modified Reynolds number, so that the 1 minus epsilon or the 1 minus e void fraction particle is also included, right? Now, to do that, you have to look at the forces on the bed. So if it has unit cross section, thickness is L, voidage is epsilon. What is the total surface area of the particles? Because the specific surface area is known to you. So how will you calculate the total surface of the particles? Because once we know the total surface, we can find the total resistance force or the drag force. So first you should find the total volume of the particles. Then using the specific surface, capital S, we can find the total area or a total surface. And then if we multiply it by the component of the drag force, which I termed R prime, that is a measure of the resisting or drag force. And then this resisting force, we must try to balance by the pressure drop across the bed. Okay. So can you work all of the expressions for each one of these individual things out? right? I have not given the steps here, so I guess I just wrote the final expression. Okay, we can outline that. Suppose the packed bed has unit cross section L length L. So volume of the particles in that bed of unit cross section is just L into 1 minus E, where E is the void fraction. L into 1 minus E, the volume. How much total surface would the bed have due to the particles? Obviously, whatever you found out times capital S. So the total surface would be capital S into L into 1 minus E. Now what drag force will be exerted on this surface? We defined the component of the drag force per unit particle area, per unit area of the particle's surface as R prime. So the resisting force would just be R prime into capital S into L and then into within bracket 1 minus E. This is the drag force in the direction of motion. Now, a few minutes ago, I indicated that this force has to be balanced by the pressure drop across the bed. Now, what you have to think is this pressure drop going to be balanced by the entire bed or only by a certain fraction of the bed? Obviously, since the flow only occurs through the interstices between the particles, we have to remove the excluded volume of the particles from any consideration when we calculate the force due to delta P. We must only consider, that is, we must only consider the free section of the fluid, free cross section of the fluid of unit area, of the bed of unit area. How much is that? That's just E. So the force then that will balance the drag force R prime into S into L into 1 minus E will be just delta P times small e. Then you can write the force balance, which is what is written in equation 8. On your screen. As follows. Now, if I want a correlation for the drag force, I can transpose this and I can find an expression for R prime, which is just delta P into E, whole thing divided through by S into L into 1 minus E. That's your equation 9 on screen. Now, if you remember, I had defined two velocities, average velocities. One was the superficial velocity and the other was the average velocity through the packed bed. And for the velocity through the packed bed, we gave the subscript 1. So it was U1. And this U1 was nothing but the superficial velocity u divided by epsilon or divided by e. So u1 was u by e. So now if I take r1 prime and divide through by the kinetic energy, just like we did for the drag force earlier in our expression, what we will get is r prime upon rho. Okay, I have removed the prime in the u here. Okay, so here I should have actually retained the prime, but doesn't matter. It's not a problem as long as you understand that the u in the denominator of this left-hand side of the equation is the mean velocity through the bed of solids. Okay, it's not the superficial velocity, it's the average velocity in the voids themselves, right? That is u in this equation. So r prime upon rho u squared is nothing but delta p e cubed upon ls 1 minus e rho u squared. Naturally, because I have put in for u the superficial, the velocity by e. So actually the right hand side of the first equality is indeed the superficial velocity. The only mistake in this equation number 10 is that I have missed the subscript of u on the left hand side, r prime upon rho u1 squared. It should be rho u1 squared because u1 squared becomes u squared by e squared, and that is how the e cubed power comes, because delta p into e squared, and then u squared in the denominator, rho in the denominator, and then ls into 1 minus e. So that then relates nicely to equation 9. Okay, now I can write this in the form that this is some constant by the modified Reynolds number. And that modified Reynolds number is just mu into rho upon s into mu into 1 minus e. So that's the definition of the modified Reynolds number Re prime. Okay, and that's used in equation 10, and k is the Kozeny equation constant. S is, of course, you already know, meter squared by meter cubed for the bed. Mu is the viscosity of the fluid, E the void fraction, rho is the density of the fluid. Okay, so what you get is equation 10. Now, you can plot the left-hand side, which is r prime upon rho u1 squared, against Re prime in log coordinates. Now look at equation 10 and see what sort of curve will you get through a randomly packed bed. We have something very similar to the type of dependence that we found under free settling conditions. Large number of experiments have been done, and what was found is, if you were to plot r prime upon rho u1 squared, where u1 is the velocity through the bed, and okay, that's I missed the subscript. Okay, sorry, I missed the subscript u1 on the left hand side, but right hand side is u, so u is the superficial velocity, so that is correct, because u1 is u divided by e, so u1 squared is u squared upon e squared. So when that's in the denominator, you will get e squared in the numerator, and e was already there in equation 9, so you will get e cube dependence. So what is found is, if r prime upon rho u1 squared is plotted against Re prime, the modified Reynolds number, first of all of the data for the packed bed falls more or less on a single curve. whatever be the size of the particles, whether they are solid spheres, hollow spheres, cylinders, they almost superimpose into one curve. They fall on one curve. Just like earlier, we can divide that composite curve of r prime by rho u1 squared versus modified Reynolds number re prime into three regions, three portions. At very low values of Reynolds number, such as below 1, the same region like what we call Stokesian region or creeping flow region. On the log-log plot, we get a straight line of slope equal to -1. Then, if the Reynolds number prime, the modified Reynolds number Re prime, is greater than 100, or approaches beyond, definitely beyond 1000. It's not clear. I mean, sometimes people say 100, some say 1000. So somewhere say 500 or so, we can say beyond 500, the slope slowly tends to 0. So we can approximate that on log-log coordinates by a straight line of slope 0. Then in between Reynolds number 1 and 500, we have the intermediate region. But this generally, instead of saying that the slope is different at every point, this region in most books that I have seen is approximated as having a constant slope of minus 0.25. Minus, well, obviously there will be a change in slope in this intermediate region between Reynolds number prime, modified Reynolds number of 1 and 500. So the slope will gradually modify, the absolute value of the slope will decrease from 1 to 1 by 4. So -1 to -1 by 4 or so in that region. And that is your intermediate region. And you will again have to use iterative solution for this region, just like we did. So I don't need to go through all of that once more. What is interesting is what I have tried to do in the next slide is to outline what we are going to find under streamline conditions, low RE. So you can take the equation 10, solve for small u, and you can derive the equation by transposition to get equation 11. What I have done is I have equated delta P E cubed upon Ls into 1 minus E into rho U squared by the Darcy's constant K times specific surface area S into mu 1 minus E upon U into rho, right? Which is what we have in equation 10. So when I equate that, U will cancel, and the square dependence of U, I mean, what was U squared is now U, and that's the left-hand side of equation 11. And you can write it in terms of all the parameters of the bed. The Darcy's law constant, epsilon or E the void fraction. So it scales as E cubed upon 1 minus E whole squared, a very classic dependence on voidage for a packed bed, for a uniform packed bed or a random packed bed, randomly packed bed. It's inversely proportional to fluid viscosity, which is exactly what Darcy found in his Darcy's law statement and by his experiments, which I outlined to you in the first class. It scales as square of the specific surface area in meters squared per meter cube for the bed. It's inversely proportional to the length, again the same Darcy's dependence, and it's directly proportional to the pressure drop. Okay. So now if you want to solve for the pressure drop, then you can solve for it using equation 11. And what do you find? You obtain, because we want a correlation for delta P. So delta P per unit length, delta P by L is 1 minus E whole squared upon E cubed into some constant, which is actually K double prime, which is a true constant for streamline low Reynolds number condition below Reynolds number 1. So as I said, this K double prime we can approximate by a proper constant. It's no more dependent on shape when you have low RE. K prime then into S squared times mu into U. So delta P by L is 1 minus E squared upon E cubed into K double prime S squared into mu into U. That's what you will get. So now if I were to solve, I want to write the equation for R prime upon rho U1 squared. Going back to equation 10. Since R prime itself was delta P into E upon LS into 1 minus E, I can substitute for that. And I shall get what you have on equation 13, which is the equation we wanted to derive. So this is an important equation. It says that the drag force per unit KE, when the U is taken as through to the bed, again I have missed out the subscript 1 in the U on the left hand side. So okay, you understand that the rho U1 squared is what is meant in this equation 13. So it scales as square of 1 minus E upon cube of voidage times the true constant K double prime, which I shall show you is which has been found to be exactly 5 for these kind of packed beds under streamline flow. Scales as square of the specific surface area divided by S, so it will scale as linearly, right? It will square, it will go linearly as S. So actually all of these terms will cancel out. S will cancel out with S squared. You will get linear with S. The E cubed will cancel with the E cubed for the U term when you put in terms of the modified Reynolds number. Then 1 minus E whole squared in the numerator will cancel with one of this will cancel with the 1 minus E in the 1 by RE prime term. If you look at equation 10 and 11 that I derived. So what you are going to get is the final term on the right hand side, which is K double prime into 1 minus E into mu into capital S upon rho into U. But that's nothing but K double prime into inverse of the modified Reynolds number, because you defined that modified Reynolds number as corrected for the surface of the bed per unit volume times and this corrected for the voidage as rho into U upon 1 minus E within brackets then mu into capital S. So this is nothing but K double prime upon RE prime. Okay, where RE prime is the modified Reynolds number that I defined, and this K double prime has a value of 5. So this equation is applicable for values of the modified Reynolds number less than about 1, that is under streamline flow. Now what happens at higher RE values? Slowly in the largest channels, because the void fractions is not always controllable, the flow starts to slowly go away from streamline flow and drift towards intermediate and turbulent flow. And then this streamline flow starts to disappear successively in the smaller channels as the value of the modified Reynolds number RE prime increases. And there will be a gradual change in the slope of the R prime rho U1 squared RE prime graph from -1 to -1/4. And then if the flow were to become completely turbulent, which probably doesn't do until Reynolds number is very high beyond a couple thousand, then that slope goes from -1/4 to 0. Okay. So in other words, what we now need to calculate the pressure drop through a packed bed is a correlation, which is called Karman's correlation or graph, just which plots R prime upon rho U1 squared or rho sometimes U prime squared, where U prime or U1 is the flow average flow velocity in the interstices of the packed bed. I already related that velocity as U by E, so inversely proportional to the voidage. Okay. And I need this R prime upon rho U1 squared or rho U prime squared. Different terminologies are used on the Y axis, which is the drag part or the modified friction factor, you may call it, for a packed bed. I want that as a function of Re prime, the modified Reynolds number, which is U into rho upon capital S mu into 1 minus E. So once I have this correlation, and if I know the modified Reynolds number and I know how much surface area per unit volume the particles have in the packed bed, then I can find the drag force, and once I know the drag force, I can calculate the pressure drop by equation what is that number? 10. Okay, you can use that. And this correlation or by equation 12. Okay, you can calculate this pressure drop once you know. No, not 12, 10, because 12 is only for streamline flow, Re less than 1. Okay, so K double prime is 5. But in general, for any other Reynolds number, you'll have to obtain the correlation, read the graph. You'll have to, I need to supply you with an analogous graph of the CD versus RE curve log-log plot. So I need to have another log-log thing of Karman's log-log plot for packed beds, which will give me the modified drag force versus the modified Reynolds number. So that is really what I have to dig out yet. I shall pass it to you tomorrow. And so then you should be able to calculate, just like we did for settling cases. For free settling, then we had a correlation for hindered settling, and now we should be able to calculate everything: velocities, drag force, pressure drop across a packed bed if we know the lengths and surface area and the flow hydrodynamics region. Okay. So what is it that we have done today is we have derived the same equation that we obtained by all in other sundry approaches, a more ad hoc approach a couple classes ago, and I have used a similar force balance type approach, and by balancing the pressure drop across the free cross section of the bed, we have derived an equation for the regime of modified drag coefficient versus modified Reynolds number, which is called Karman's graph, and I can use that to find velocity, or better still, generally it is used to calculate the pressure drop across packed beds. So I'll give you this log plot tomorrow, and in a way that's where we want to reach, because the next topic, you see, this is the problem, is that all beds don't remain packed. As the flow rate starts to gradually increase, the void volumes in the bed starts to increase, and there is an incipient point when the bed is no longer packed, and that is then called a fluidized bed. And for that we need to do the force balance afresh, anew, and then we will get similar equations, little modified from what I have given you, and we will have a new set of log coordinates plot, and on the same lines we can find everything then about the fluidized bed. What is the length of the fluidized bed? What is the point of incipient fluidization? At what fluid velocity that happens? What is the force balance under that incipient condition? Because that's only when we can do that balance exactly. And then what sort of pressure drop is there in that bed? So we can extend this analysis to a number of other industrially important cases. And then I shall give you, that is of course after minor, we also want to do the Kozeny type approximation, which is very often used for pressure drop calculation. But for the minor, we are going to stop at the for the Karman treatment of uniformly packed beds. Okay, so tomorrow, and I am going to put a notice that 3 p.m. Is the minor, about 40 odd minutes, and tomorrow I shall upload you the graphs that we will require to be used.
Sir, can you tell the book which which we can follow for some questions?
Basically, a lot of books are available now. The book I have used is Coulson and Richardson. That is for packed beds, but it doesn't give a great thing on fluidized beds. So, you know, either one possibility is we use Faust's book on unit operations. Alternatively, for fluidization, we can use McCabe's book. I haven't decided on that, but this particular thing is well done in Coulson Richardson's book. But you are going to find similar things in with different notations. So you can, if you want the same notation, please use the slide. Only error in my slide is on the left-hand side. It's not small u, but u prime or u1. So when I give the correlation graph, I will of course correct it. All right, I just saw that one error, that the subscript on the left hand side has been missed, but everything on the right hand side is correct. Okay, we'll conclude tomorrow, and I'll put a note today only right now that minor will be from 3, so you should definitely log in few minutes before. All right.
Sir, rather than preferring for a book, just give us some few questions so that we can have a look on what all are the things that needs to be covered apart from slides.
I generally don't do that now for third year, fourth year. I only do that for second year, first semester. I don't do
Okay,
it.
sir. We
Yeah.
will refer the book
You will
only.
refer, you will manage, you will, there's a lot of all this material is available. The only thing is each one has its own way, and I have tried to cover it a little bit my own way, because I was constrained by what I started out with, you see. So you whatever you can follow. I mean, I kind of like this because is in sync with what we started out with, right? So different books are going to do this differently. So you don't want to look here, there, and 10 places. I mean, finally, it's the same equation. All you need to do is use the correlation or the graph, log plots, and calculate delta p or drag force or velocities, etc. I mean, that's all that you need to do. It hardly matters how which book or which equation finally we use, right? Okay, I will complete this tomorrow, and I'm just going to put a notice about the minor, and so that it's available on Microsoft Teams. So please tell everybody I don't. There's nothing like makeup or anything like that anymore. Yeah. So there's no makeup minor. So you miss it, you miss it. So I'm going to put the note right now. Okay, 3 o'clock for 15th. It's correct, right? Our slot is H, right? Himanshu, our slot is H slot, correct?
Yes, sir.
So
Sir,
it
our
will be
slot is H
so
slot.
3 p.m. is correct, right? On Monday,
Yes,
15th.
sir.
Okay,
Yes.
I'm going to put that because I don't want to make a mistake. I've started to forget which is H, which is J, which is because we are no more in that mode, and because of this online thing. Okay, no problem. I'm just going to post it. All right. See you tomorrow, and we will conclude everything for the minor.
Okay.
Okay. Thank you very much, guys. Thank you.